let's review momentum. Remember, the momentum of an object is defined to be the mass of that object times its velocity. So say I have a block of mass, 10 kilograms, and it's moving to the right with a speed of 3 meters per second. Then I could find its momentum to be its mass, or 10 kilograms, times its velocity, which is 30 meters per second, or it has a momentum of 300 kilogram meters per second. Let's suppose I have this same block and it's traveling along nice happy speed, 3 meters per second, and it hits a brick wall. Clearly, at the brick wall, its final velocity is going to be 0. So, the momentum after it hits the wall is going to be its mass times its final velocity, which is 0. So, when my block hits the wall, it has a momentum of 0. We see we've had a change in momentum of, let's see, this is P final, or P2 minus P1, 0 minus 300, or negative 300 kilograms meters per second. So we've had a change in momentum. Now, depending upon how long this took and how much force you hit it with, that will definitely change what happens to your object. So let's look at that. We are going to analyze momentum problems with what we're going to call impulse. And we're going to define the impulse to be J, sometimes we use it as I, it depends upon your book, is equal to the force applied times the time of the impact. With an impulse, there must be an impact of some sort. So in this case, the car is moving along at 5 meters per second, and it hits the wall, and it stops moving. In order to change the momentum, we have to apply a force of some sort over a period of time. And so we have to apply an impulse. Now, in this case, can we calculate the momentum change? Well, the change in momentum is the mass times the final velocity minus the mass times the initial velocity. Let's, just for convenience sake, give this a mass of 1 kilogram. Then the change in momentum is going to be 1 times 0 minus 1 times 5, or negative 5 kilograms meters per second. Now that negative sign just gives us direction. But what if we wanted to know the impulse? Remember, we defined impulse is force times time. Ooh, let's try an impulse, not an F. Impulse is force times time. So we know there's going to be some force applied over some time. Clearly, more damage would be done to the car if the force is large than if we have a small force. The change in momentum was easy to calculate for this problem, but the impulse isn't so easy. Let's see if we can find a relationship between this change in momentum and impulse. First, let's look at units. The units for impulse, let's see, force is measured in newtons and time is measured in seconds. So the units for impulse are newton seconds. Let's discuss the impulse momentum theory. This is a theory that is going to connect your impulse, your I equals Ft, to your momentum, P equals mv. Let's go back to the original Newton's second law, F equals ma. We have this down. Now, suppose we take acceleration, and we know acceleration is change in velocity divided by time. So suppose I take that and plug it in for my A. I can rewrite this as the force is m times the change in velocity over time. Now, everyone in my class knows I don't like to mess with fractions, so let's get rid of the fractions here. I'm going to do that by multiplying everything through by t. So ft equals, let's see, that t is going to cancel, m delta v. Wait a second. Ft is what we just defined to be impulse, while m delta v is our change in momentum. So I have just mathematically shown you how to get from Newton's second law to what we're going to call the impulse momentum law, P-L-S-E, momentum. And basically what it says is that an impulse, if I have an impulse, so I have a force applied over a period of time, it will cause a change in momentum that is equal to the impulse applied. Now, what this also means is if you do not have an impulse, if you have no force applied, then you're not going to have a change in momentum. So your object is just going to keep going on at its steady speed. So, rewriting, Ft is equal to the change in momentum, or m delta v. It doesn't matter which way you write it. Let's look at this. We have a green car and a red car, and they both have the same mass and the same initial speed. So we know the momentum initial for both of them is the same. Now, the green car stops, so it has a final momentum of 0, and so does the red car. The red car has a final momentum of 0. And so we see the change in momentum of these, which is equal to P final minus P initial, are the same. Both of these cars have the same change in momentum. However, we know from experience that the ride in these cars is different. If you look at this, the change in momentum of the green car is Ft, while the change in momentum of the red car is Ft. I think it should be fairly clear to see that, let's see, the red car is going to have a much larger time to stop, which means you will wind up experiencing a smaller force, as opposed to the green car, which is going to stop in a very short period of time, and so you'll feel a larger force. Basically, the red car taps the brakes slowly, and you stop at the stoplight without jostling your coffee all over the place. While in the red car, you slam on the brake, the green car, they've slammed on the brakes and everything goes sliding around. But the change in momentum is the same. Even though the change in momentum is the same, the force is felt to be very, very different. Now we say that the red car is actually stopping more safely because it takes less force to change momentum. This is also much better on your tires and on your brakes. Now, let's look at this boxer. We've got his opponent is coming in, and his opponent has some initial velocity of his glove. Doesn't matter what it is. And his final velocity of his glove is always going to be 0, because he's going to smash it into my boxer's face. Now, the change in momentum is going to be the same in both of these cases. The question is, in which case does a boxer's nose get broken? In the first case, the boxer is rolling with the punches. He is stepping back. He is increasing the time of impact, and this is decreasing the force of the glove on his face. While in the second case, he's trying to get this punch over with. He's leaning into it. He is decreasing the time of impact, and that is greatly increasing the force of impact. This guy will need nose surgery when this one's over with. Now this guy, I don't know if he's trying to increase his time and therefore decrease the force if he should fall, or just guarantee he's going to fall. But that tire right there will definitely increase his impact time should he fall over. Playgrounds have always put down padding so that when little ones fall, we're increasing the time and decreasing the force so the little ones are safe. The exact same principle is true with airbags. With your airbag, you hit it right here, and it hurts. Don't get me wrong, it hurts to hit an airbag, but you're increasing the time of impact, and therefore, let me do it this way. Okay, you're increasing the time of impact and therefore decreasing the force. And that is why airbags save lives. Bungee cords, same thing. As he falls down, as soon as it snaps tight, he is going to greatly increase his impact time and decrease the force. So, how could you use the impulse momentum theory when you want to maximize an increase in momentum? Well, why would you want to maximize an increase in momentum? Well, it's clearly if you're trying to get something moving and trying to get it to change its velocity more. Basically, you're going to want to maximize both force and time through follow-through. Some real-life examples, well, golf, football, baseball, pretty much any sport, you're going to want to increase the time by what the athletes call follow-through. And if you want it to go as far as possible, you're going to want to throw it with as much force as possible. Now, we can also use the impulse momentum theory to cause changes in momentum. For example, if we increase the time of impact, we can change our momentum more safely by decreasing the force. Usually when we're talking about people and safety, this is what we're wanting to do. We can also increase both the force and the time to get maximum change in momentum as what we do with most sports. Now, there is another application. We can decrease the momentum over a very short period of time. And what you usually wind up with is a very large force and a crash. Whenever you have a very, very short time, you're going to have a large change in momentum. That's usually going to result in a very large force.